Okay, so thank you everybody for joining us today. Well, we're excited to have Mine with us today and talking about teaching and learning Bayesian statistics with Bayes rules. This meetup is hosted by the Southern California Art Users Group and Our Ladies Irvine. So we're excited to have a dual event. So just the agenda here real quick. I'm gonna go over some welcome and announcements, and then we're gonna go over the talk. I have it as 6:05 to 7. That might go a little bit shorter depending on questions and all that. But that's the agenda. We want to thank our sponsors. We have the UCI Palmerage School of Business as one of the sponsors for this meetup, where we've been working with them for over a year now, and we're very glad to have them as sponsors. We also have another sponsor, which is UCI Master of Data Science. Again, very grateful for all their support and happy to have them as sponsors. So a few announcements. So SoCal ROG, we are now a nonprofit organization. It took some time to set this up, and you know, a lot of busy paperwork and all that, but we're very glad that we got that done. This will allow us to continue growing and supporting people and groups and growing the community here in Southern California. So we're grateful and excited that we were able to achieve that. Some of the events that we're gonna have in November will be announced very soon. We're still in the works of coordinating the event and speakers and all that, but we'll announce that soon. And as I mentioned, this is a dual event. We're co-hosting with Our Ladies Irvine. Madeline, we have Madeline here, and Alisa Columbus, she's the founder and organizer of Our Ladies Irvine. I don't know if any of you want to say any words here.
Sure. Thank you, Pablo. Yeah, it's a delight to co-host this event with you guys, and looking forward to future collaboration.
Great. Thank you. So just, if you're new to Our Ladies Irvine or SoCal ROG, these are some of our links and ways that you can connect with us. We have websites, we have GitHub, Slack, YouTube, Twitter, LinkedIn. So that's, if you want to get involved, please reach us out through those links. This is going to be recorded. We're going to upload this to YouTube, so don't worry. You can press pause later on and get the links there. Okay, so to the talk, we're excited to have Mine with us today. She's going to be speaking about teaching and learning Bayesian statistics with Bayes rule. So I'm going to hand it over to you, Mine. I'm going to stop sharing, and then let me know if
sure. I also just posted the link to my slides in the chat if anybody needs them for future reference, but I'll go ahead and share them as well. Thank you for having me, Our Ladies Irvine and SoCal ROG. So a little bit about me. I'm at UC Irvine in Department of Statistics, and I'm an assistant professor of teaching. And I'm also the vice chair of undergraduate studies. You might realize that this talk and generally in my academic life, I'm very teaching focused. And also I realized that one of the sponsors of this meetup, which I had no idea about actually before, is our Master's in Data Science program, which I'm also teaching at. So I teach undergraduate level, and I teach also graduate level as well in statistics and data science. You will mostly be seeing me today, but the work I will be presenting is a collaborative work with Alicia Johnson and Miles Ott. In addition to this work, I think they're just generally like really good academics and Miles no longer is an academic, but they're really good people. If you don't know them, I would really suggest that you check out their websites and profiles. So today I will be talking about, like, the title of the talk sounds like as if I'm only talking about the package, but it's not just the package. Actually, there's a book accompanying the talk, and I will actually talk about the book, and then I'll move on and talk about the package, how that package supports learning Bayesian statistics. And of course, I have to make assumption about who you might be, why you might have ended up at this meetup. So it's possible that some of you actually might be teaching Bayesian statistics or wanting to teach Bayesian statistics. And when I say people teaching Bayesian statistics, I don't necessarily mean people who actually just are teaching a full course on Bayesian statistics. It might be that they're teaching different courses and just want to include some Bayesian topics in them. Whereas for many of you, I think that you're in industry, so you might be actually teaching colleagues possibly on Bayesian statistics. Or you might even be teaching yourself using these tools. So either of these scenarios would work. But because I'm so used to teaching in a classroom and teaching to my students, so you might hear me say things, but you can just tailor that in your mind for your own context if you're self-teaching or teaching your colleagues. For anyone who is here, I thought, who's never probably seen Bayesian statistics, I thought I would start off with an example, a very basic foundational Bayesian example, just to give an idea of how Bayesian statistics is different than probably what you have been exposed to, which is the frequentist paradigm. So if we assume pi as the proportion of spam emails, and if you try to estimate pi, we will assume that pi can be any value between 0 and 1. So what makes a Bayesian modeling different is we always start with a prior idea. We ask ourselves what pi could possibly be, and we also ask ourselves how certain we are. So we are actually have some idea about the variance starting the problem as well. So if you were actually approaching the spam email problem, wondering the proportion of spam emails anybody gets, you might, if you were taking a frequentist approach, you might perhaps go with maximum likelihood estimation. You observe some data. Let's say we observed 10 emails, and out of those 10 emails, 3 of them turned out to be spam. So you might see that the likelihood function maximizes when pi is 0.3, 3 out of 10. So that does not mean pi is 0.3, but if we had to bet any value, it's most likely 0.3, but pi could be other values too, 0.5, even though that's less likely. So this approach, just focusing on data, let's call it frequentist approach for now. However, in Bayesian statistics, we also have a prior model that we have some information about anything we are trying to estimate even before we collect data on it. So when I told you about spam emails, you all might have had your own views about proportion of spam emails. So some of you might have thought that range is quite wide. You're not very sure about your prior idea about pi, but you're assuming that it's somewhere in the middle range that's more plausible. Some of you might have been very certain that pi is a small value. So you might have had a prior idea that is closer to the plot on the right. So these are just some prior models that anybody could have had. So what is happening in Bayesian analysis is we actually get to a posterior model based on our prior we've started with, and the likelihood based on the data that we've observed, and a combination of these two make us arrive at our posterior model. Maybe in this figure, it might be a little bit easier to see. You can see that the posterior, which is the green plot, actually falls somewhere in between the prior and likelihood. So if somebody had started with the prior assumption that the pi values are on the smaller end and they were very certain about it, by the end of observing the data, they actually changed that belief a little bit towards the higher values of pi and a little bit less certainty. So this is, in essence, what Bayesian modeling is about. We start with a prior idea. That's what we have in addition to likelihood. And then we arrive at posterior. So getting back to the book, the target audience of the book is advanced undergraduate statistics in advanced undergraduate students studying statistics or data science. But we're also aware that not everybody is lucky enough to have a Bayesian course at an undergraduate level. Most of us are not trained in Bayesian statistics at undergraduate level. So we are also, we've designed the book to be available to somebody who is equally trained, but actually practicing statistician or data scientist, but not necessarily trained before. So what we mean by equally trained learner is someone who has done some prior course in statistics, would be able to pick up this book, hopefully. But if they're familiar with probability, calculus, and phi-diverse, it would be a little bit easier for them to pick up this book. So however, probability and calculus and phi-diverse is just recommended. We know of learners who have read this book without having had some experience behind all these. So we try to make it be as accessible as possible. But it's also not a first course in statistics. So definitely not a first course, but some familiarity should go a long way in this book. I should also mention why we even wrote this book. So we know that Bayesian methods are becoming more popular. For those of you who are in industry, you might even realize more jobs popping up in job ads, specifically asking for Bayesian modeling techniques. And one of the reasons that Bayesian statistics is getting quite popular is because it's computational heavy modeling. And in the past, we did not have such computing resources, as much computing resources. But the more computing resources we have, the more we are able to fit Bayesian models, or easier. And also in the past, Bayesian methods generally have been criticized for being subjective. I'm not going to say everybody would agree, but I think since the former years, we've come a long way on that too. So there is less criticism on that, but that criticism still exists. So Alicia, I, and Miles, we were all teaching these courses in Bayesian course for undergraduate students, but we all sort of patchworked from other textbooks because most of the textbooks in the market were for more advanced learners. So we wanted to actually have a textbook specifically targeting beginner Bayesians. So to give an overview of what the book looks like, I'll go over through the 4 units, the main units of the book. So we start with the Bayes rules in the first unit, and then we start with the beta binomial model. So the beta binomial model is the example I have shown in the SPAM example. So the prior in that case was a beta distribution. The likelihood was based on a binomial, and the posterior is also on a beta. So this is really one of the simplest models in Bayesian statistics. This helps us also teach learners other aspects of Bayesian statistics. For instance, understanding the posterior as the balance between prior and likelihood, and also understanding how sequentiality works in Bayesian statistics. In other words, what happens if we collect data sequentially versus what if we collect data all at once? But this simple model can help us see all these aspects of Bayesian statistics. Beta binomial model is one of the conjugate families, but we also have gamma Poisson and normal in the book too. Those are some special models as well. Once we actually work with models that are easy to calculate, we then move on to the models that are not easy to calculate, basically the models that would actually require simulation, where we cannot exactly specify the posterior. So there are 2 algorithms we use. One is grid approximation, and the other one is the Metropos-Hastings algorithm. So this actually does more into the logic behind how posterior simulation works in Bayesian land. And once we approximate the posteriors, then we actually use them to do a posterior estimation of the mode, expected value, and so on, and do more things that are you might all remember from frequentist land, like hypothesis testing, credible intervals, not confidence intervals, though, and so on. And then we move on to predictions. Unit 3 and Unit 4 would be more classical modeling sense because they're more based on linear models that usually perhaps those who are just picking certain chapters might be interested. The third unit is based on regression and classification, including normal, Poisson, and negative binomial, logistic, and naive-based classification. And then we move on to hierarchical models, both normal and non-normal. I should also note that these are a lot of chapters. If anybody's teaching, or if anybody is learning themselves, the chapters by themselves could be used standalone, some of the chapters. So for instance, Alicia teaches in a semester system. I teach in a quarter system. I don't get through all of these chapters myself. So when I'm teaching, so for instance, I skip from normal regression to logistic regression and skip Poisson and negative binomial. Pablo, can I kindly ask you to mute participants if you don't mind? Sorry, it's getting a little bit distracted. Thank you. Sorry about that. I think it's just left on by mistake. I don't mean to mute anyone in that sense. All right. So that was the overall, like the content of the book, but in terms of pedagogy, I'll mention a few of our approaches to how we've done. And I think this is, for those of you who might just be here because you're a learner, I think in general, learning probability or probabilistic thinking or Bayesian thinking, one thing that's very useful is checking intuition. It's very helpful for two reasons. Sometimes our intuition is right, sometimes it's not right. Either way, it's helpful to check intuition. So I'll give an example. For instance, one of the examples in the book is about fake news. Reading an article and deciding whether it's fake or not. So our prior information is that 40% of the articles are fake. And then we have data that exclamation marks are more common among fake news. And then we observe one article and it has an exclamation mark and we have to decide whether it's fake or not. So we have to, that's our posterior. So we have to ask the student or the reader or the learner what their intuition is first, given this prior and this data. They might be right, they might be wrong, but at least checking intuition first gives them a way for them to assess their learning, how their ideas are changing, how their probabilistic and Bayesian thinking are changing as they're learning. And then they can go back and say, think about, was it very correct? Why not? What did you learn throughout the process? Another thing we have tried to do is active learning. This is a lot easier. Active learning is generally hard, but it's a lot easier in classroom than it is in a book. So we never know if the reader is actively reading it or not. So we kind of provided opportunities. If they choose to do active learning, they can. One of them is by quizzes. There are plenty of quizzes throughout the book within text, and they're usually short, just 1 or 2 questions to have checkpoints for the reader to make sure they're on track, what they think, and so on. And another thing we have done is we actually have code within text because we hope that the readers will code as they are reading, or at least try to understand the code output to see what is happening in the data analysis part. Also, I've linked I've linked the Metropolis Hastings algorithm in case anybody wants to dig into that. But I also linked a quiz here for anyone to quiz themselves if they choose to. So this is one of the first quizzes. So this is the longest quiz perhaps in the book. Normally they're very short. But this is a quiz that provides the first step to see if you're Bayesian or frequentist at the beginning. And it's not like we're giving trophies if the students start Bayesian already. The idea is not that, but just to see the differences between Bayesian and frequentist thinking paradigms, how they approach the idea of probability of an event, how they approach hypothesis testing, how they approach claims in general, and the idea of chance random process in general. So if you would like to test yourself, if you're already Bayesian or frequentist, please be my guest. And throughout the book, we tried to have computing and math together. And if you had to make a choice, it's computing first, then followed by math generalizations later. So for anybody who might be scared of calculus or formula, don't worry, they come towards the end. And hopefully they make sense once you actually code that and walk through all the steps. The formula and the notation makes much more sense, so that you're not faced with just like some Greek secret code at the beginning. And our approach to computing also, we wanted to make sure that students or learners first compute themselves for a single case. They need to know what the algorithm is doing. They need to know how the predictions are done. They need to know how the classification is done. But once they can actually do these, they can then move on to built-in functions, because these computations from scratch takes lots of time. If there are built-in functions, they should be able to use those, but they should also know why those calculations are happening the way they're happening. Why are they getting that result? So this has been our approach. And perhaps the most important thing for Alicia, Miles, and I, when we started this, was we want to make this book as accessible and inclusive as possible. And to be honest, we know nothing. I shouldn't say we know nothing, but we're not trained in accessibility and inclusion. So we had to do our homework. And to be honest, we've spent time thinking about this, reading about this, and we're still learning. So I'm not actually presenting this as an endpoint, but this is part of our process, how we approach making this project. And I thought this was important to include in our meetup, because I know there are many of us who actually, like, you may not necessarily be a college professor like I am, but I know many of you are making resources online or giving talks yourself. So I hope this framework can help other R users in general in their work as well. So in terms of accessibility, we wanted the cost to be affordable, and Madeline asked this, so I'll answer this. The book is open access, and it is set to come out in January from CRC Press in print. And Madeline was wondering if it will be available still free online, and the answer is yes, the book will always be free available online. Another accessibility criteria we had was whether the plots would be distinguishable for colorblind users. So we specifically picked a color palette that would work. We also wanted to provide alt text for blind users who might want to use the book. And at the time we started writing the book, actually alternate text was not possible because we were using Bookdown, and knitr package did not support alternate text. But we actually requested from knitr team to have this feature, and now knitr package actually supports alternate text. So that's also possible, and we have alternate text for all images in our book. Also, the field of statistics and data science is quite diverse. We wanted the book to be reflective of the scholars, diversity of scholars in the field as well. So we paid close attention to who we are citing, whether they represent the diversity of the scholars in the field and their experiences. And we made sure that we don't name any trans scholars, because good, like academic scholars, websites, they might be a little bit misleading, because they usually do web scraping. And we also wanted the book to reflect the diversity of students or diversity of the readers. In many cases, we tried to avoid specialized knowledge from like too detailed sports analytics. We avoided too detailed medical examples. We avoided, because these are some areas that require like maybe half a page of introduction first, then the user can get to the data. We try to use diverse names and pronouns as much as possible. We also considered we usually work with younger students, but our readers might come from older generation, and our students are not always young either. And also overall, all of us, Alicia, Miles, and I, like, we're not perfect learners. We embrace mistakes, and we try to reflect that to the readers as well. And we have actually written a full preprint on this, our approach to this. You're welcome to check it out if you're interested. I'll then move on to talking about R packages. I believe everybody is most interested in this part, what we use. So I'll first talk about the bayesrules package. It is on CRAN, and you can also check out the development version if needed on GitHub. So I have already briefly talked about some plotting functions, like plotting the beta distribution. So this plotting functions actually helps the learner first initially how to specify prior model. So by changing the alpha and beta arguments, the user can actually see, is my idea more reflected with the plot on the left or on the right? And they can tweak some more values. We've also seen plot beta binomial, which actually is the full beta binomial model. It's not just the prior, it's the likelihood and the posterior. So in this case, they actually can include information based on their prior alpha and beta, as well as the observed data, number of successes Y, and number of trials, and for the binomial model. So you might be thinking, like, where does this all these visualization get the learner? It gets the learner these like easy usable functions, gets the user to the bigger picture of the Bayesian story. One of them is what happens when sample size gets larger. So when we're actually comparing the columns in these plots, we're actually looking at the case where sample size is increasing, but the proportion of successes is staying constant. So then the learner is able to see when sample size, when there's more data, the posterior is getting closer to the likelihood. They can also compare what happens under different prior scenarios. So each row, for instance, is a different prior model. So by looking at this plot, students are easily able to see that when we have a flat prior, like beta 1,1, or you might know it as uniform model. So when there's a uniform prior, you can see that the posterior is just based on the likelihood and posterior overlap. So in other words, there's no contribution of prior to the posterior model. So these small visualization functions help the user, first learners in Bayesian statistics, try different prior scenarios, try different data scenarios just to see the effects on the posterior. And it also helps them see the sequentiality as well. So I've been talking a lot about the beta binomial model, but beta binomial model is not the only model. In the package, we also have gamma Poisson and normal, and you will see that the patterns are pretty similar. First the prior, then the likelihood, and then the full model plotting. In addition to plotting functions, one thing that helps students, learners understand is the expected value of these models, prior and the posterior, as well as the mode and the variance as just in general summary functions. So for each set of these models, we also have the summary functions available. So everything on this slide is basically helping learners lay out the foundations of Bayesian statistics. But once they understand the basics of Bayesian statistics, and they're actually like modeling data in linear models at least, then we have set of model evaluation functions that makes the process a little bit quicker. So we have three sets of functions. The first set is for normal regression models. The second set is for logistic regression binary outcomes. And then the last one is for naive Bayes classification. And just to give an example of how these evaluation models work, for instance, for a normal regression model, let's assume we have a model, some Bayesian normal regression, and then we have some data, and I'm specifying some credible intervals. So you can, if you're not familiar with the term, you can think of it as if it's confidence intervals. So 60%, 80%. So, and what I'm trying to do is get some sort of model evaluation criteria. And in our case, we are trying to see how bad the model fits. So we are looking at median absolute error or the scaled version of it. And we're also looking at how many of the predicted values fall in within the 60% posterior predictive interval and 80%. We also have the cross-fold validation version of these modeling functions, model evaluation functions. So in the case on the right, we are doing two-fold cross-fold validation. So we get the same model evaluation criteria for each fold separately, and we get overall model evaluation criteria as well. So this was all about Bayes rules, and we've specifically designed Bayes rules for teaching Bayesian statistics, the first set of functions, and then the model evaluation functions. And the data sets in the book are in there. But we don't only rely on Bayes rules, the book goes beyond that. For posterior simulation, we use RStan. So RStan actually has its own, uses Hamiltonian to approximate the posterior. And if you look at the R-stan code, you will realize something. On the left, actually, let me briefly, for anybody who, this might look a little bit scary if it's the first time you're seeing R-stan, let me pause a minute. So this is a regression model, normal regression model, and we're trying to predict number of bike rides, Y, and we're predicting it by temperature of the day using the bikes data. So this is your regular one simple normal regression model. You might realize the likelihood. This is a normal model with a mu centered at beta 0 plus beta 1 times x, and you have the variance term as well. But what we will notice is that the code on the left, where you're actually defining the details of the model, what beta 0 is, what beta 1 is, as well as your variance term. You're also defining the data, how long your y vector is, how long your x vector is, and so on. So this is not a code in R. So students who are using this for the first time might be a little bit hesitant to switch to STAN easily. So one solution to that, in case anybody is hesitant to learn anything like this, is to use R-stan-R. This is a much easier way for a beginner to be, if the syntax is difficult for STAN, to be familiar with fitting Bayesian models. And this is a lot more familiar with those of you who have seen the GLM function before in R. This is just a STAN underscore GLM version. So we do have the Y tilde X much closer aligned with R. So what do we do in Bayes rules? Because we have students who need to know the both, and we think readers can know both as well. So in situations where students are trying to understand how posterior is simulated, because after all, you're trying to approximate beta 0, you're getting simulations for beta 0, beta 1, and sigma. So specifying STAN helps learners learn what is going on the back end much easier. But at the same time, once they understand how posterior simulation works, we are doing so many things with posterior distributions. We are actually doing posterior predictions, we are doing posterior classifications, and so on. So what we do is we introduce our STAN, but then once we get to using posterior distributions, we move on to using R-stan-R. And so if you're a little bit put off by R-stan, I would still recommend you to use R-stan-R, but R-stan is not as scary as it looks the first time you see it. Another really useful package that we find in teaching Bayesian statistics is baseplot, because you're getting so many simulations from our STAN model. Even if you use R-stan-R, the output is still like so many simulations. To make meaning of these, plotting usually helps, and baseplot provides some plotting functions that makes it like easy as what you see on the screen to be able to just look at your outcome. So for instance, just by looking at the density overlay of model, you can see we've simulated approximations for 3 parameters: intercept, temp, the slope, and the sigma in the model. And we can see densities for all of these approximations. And same with trace plots. Some of you might know these as caterpillar plots. So they also, the base plot has amazing wrapper functions for both of these. And in addition to packages, I'll share a few resources before I get to the end. I don't know how many of you actually teach at undergraduate level, but if you do, there's like a list of undergraduate Bayesian education resources website. And we also have an undergraduate Bayesian education network. If you're teaching Bayesian at the undergraduate level or would like to teach it, you're welcome to join this network. And last but not least, I teach a course Stats 115 at UC Irvine. This is the senior level data science requirements as part of our major, but non-majors also take it. And before I finish, I want to mention one project that I think might be of interest to others here, which is the SoCal Data Science project. It's an NSF funded project. It's actually generously funded by NSF. We are grateful for that. It's a collaboration between UC Irvine, Cal State Fullerton, and Cypress College. And as part of this project, I'm only telling you the Bayesian part of it since my talk was about Bayesian. But Cal State Fullerton will also develop and implement a course similar to our 115 course, which is basically based on our Bayes rules book. But the project itself, the NSF project, is much bigger than the Bayesian course itself. We do have data science fellow students, and they get to work with real data with our academic and industrial partners. They do have some Bayesian or non-Bayesian projects. And if any of you are in a situation where you would like to hear about these projects or would like to partner, we could talk and we could make it a win-win situation for your company or your workplace and our students as well. That's all from me for today, and I'm happy to answer any questions.